Hi, this is Shaohui Liu from ETH Zurich. Today I'm going to present our CVPR project 3D line mapping revisited. In this project, we present a robust and scalable pipeline for mapping 3D lines from multi-view pose images. We improve over all stages of line mapping, resulting in high-quality 3D line maps with track associations. The system can also utilize the 3D-2D correspondences from the point maps to further improve the mapping quality. Here shows some examples of the produced 3D line maps from our system. The pipeline is robust and scalable, such that it can work reasonably well on in-the-wild multi-view image collections or videos. The availability of the good quality 3D line maps also open up new possibilities to multiple applications, including hybrid localization, bundle adjustments, and line-assisted multi-view stereo. The full package is open source with modular components and Python bindings. Modern multi-view geometry software mostly rely on feature points. However, it often struggles on man-made environments such as indoors and outdoor buildings due to lack of textures. Here shows an example of the indoor 3D point mapping with a strong superpoint feature detector and co-map point triangulator. Though thousands of points are triangulated, one can barely recognize the room layout. On the contrary, a handful of 3D line segments already suffice to describe the full scene layout. Those lines often lie on the geometric boundary that delineate the homogeneous regions where the point features struggle. Moreover, we can move one step further to model some mid-level structures with the line features, such as the point-line association graph and the line-line parallelism. Thanks to the advance of deep learning, there has been tremendous progress on the detection and matching performance of line features. However, compared to the point case, the mapping of lines does have its own challenges, including inconsistent endpoints across views, line fragmentation, lack of two-view geometric verification, and weak matches. Finally, but most importantly, line triangulation itself intrinsically suffers from degeneracy, such that one can get highly unstable triangulation from nearly perfect detections and matches, making the 3D line mapping problem highly tricky that often needs supports from the third views for cross-verification. For example, one cannot triangulate all the horizontal lines with pure horizontal motion because all the back-projected planes are overlapping. One idea to mitigate the degeneracy is to use the stable point triangulation from the association graph between points and lines. This graph can be easily constructed on 2D and propagated onto 3D if 3D-2D point correspondences are available from an existing point map. Here shows a brief overview of our mapping pipeline. With a set of multi-view pose images as input, we first perform detections and matchings in 2D. Then, we generate 3D line proposals by triangulation, score and merge them into tracks, and finally apply joint optimization to get the final line maps. At triangulation, aside from the algebraic line triangulation, we can also use the point-line association graph to get stable 3D points lying on the line, which helps resolve 2 degrees of freedom to avoid degeneracy. Same strategy also applies to vanishing points, which helps fix the 3D line direction. Next, we compute if there are additional supports on other views to filter the unstable triangulation and get the best 3D assignment for each 2D line, followed by merging supports into 3D line tracks. Finally, a joint optimization is applied on all the mapped 3D lines to get a final accurate line segment that aligns with its 2D supports. This optimization can also come together with additional residues on point-line associations and line-line parallelism. The optimization on the mid-level associations also enable byproduct outputs on point-line association graphs and line-line parallelism. From the association graphs, we can also extract local planes and multiple Manhattan axes, resulting in an Atlanta world. Here, we show more results on the extracted 3D line maps. As the whole system after feature detection and matching is learning-free, the proposed method does not suffer from the generalization problem. Here, we show example comparison with the only existing line mapping software, Line3D++. Our method does not have those noisy lines flying around the space and can recover subtle details such as the line lines on the ground. Here, we show more comparison with the very recent mapping method last year, where our method produces much more complete and accurate 3D line maps. Quantitative evaluation also shows that our method outperforms existing ones by a significantly large margin, particularly on the track quality, which is very important to applications such as visual localization. Here we show a large-scale line map of Aachen. The mapping part is linear to the number of images, which takes less than 10 minutes, showing very promising scalability to large datasets. Here, we show another example on the classic Rome dataset from BigSFM. Here are more examples of our line maps. Our 3D line maps open up new possibilities to many downstream applications. One of the most intuitive ones is localization. Lines are very suitable for localization thanks to its gradient light detections. By optimizing the reprojection error, we can achieve very accurate pose estimation. We implement a hybrid localization framework using both points and lines. By combining 4 different minimal solvers into a hybrid runset, we can get more accurate localization results, especially indoors, where the feature points are often sparse and ill-defined. This is further verified quantitatively, where our hybrid point line localization pipeline achieves consistent improvement on multiple public benchmarks, with either RGB or RGBD images as the input for the line mapping process. We also build the 3D line maps on the new large-scale dataset Lamar, where the improvement of line features is again significant. Aside from localization, we also try to optimize the points lines jointly with the camera poses and intrinsics in a hybrid bundle adjustment framework. Again, integrating lines alongside points yields the best performance. Further extensions also include using lines to assist dense mapping and feature metric optimization. We also use the mapping pipeline to benchmark existing detectors and matchers, which provides a lot of indicative information on the behaviors of different alternatives. We are now integrating the components into a hybrid incremental SFM pipeline. Stay tuned on the new updates. Thanks for the attention, and welcome to check our poster on Thursday afternoon.